Hello and welcome back. In the previous video, we were discussing the continuity equation, and basically what the continuity equation says is it says that the rate that water flows into a pipe has to be equal to the rate that the water flows out of the pipe. So if we look at this pipe down here, for example, as the pipe gets narrower, the water has to speed up so that the rate that the water is flowing in is equal to the rate that the water flows out. And towards the end of the video, I pointed out that in this section right here, where the size of the pipe is changing, the water must be accelerating, since the water is moving more slowly through the larger pipe on the left, and it's moving faster through the narrower pipe on the right. I also pointed out that because the water is accelerating, this means that there must be a net force that is acting on this water, and this means that the pressure over here on the left has to be higher than the pressure on the right. In this video, I want to talk about how we can actually calculate what that pressure difference is between the left and right side of the pipe. And the way that we're going to do this is by using the work-energy theorem. So we'll actually calculate the work that's done on the water as it's being pushed through this pipe, and we'll relate that to the change in the energy of the water. Now, because we're going to be using the work-energy theorem to relate the work that is done by the pressure in the pipe to the change in the energy of the water, not only will we be able to relate the work that is done by the pressure to the change in the kinetic energy of the water, but we'll also be able to relate the work that is done by the pressure to the change in the gravitational potential energy of the water. And this means that when we do this derivation, not only are we going to come up with a relationship between pressure and the speed that the water is flowing through a pipe, but we'll also find an alternative way to derive this pressure-depth relationship that we found in the previous video. So how do we actually calculate the pressure inside a pipe? Well, let's consider this example that I have over here on the right. And we can see in this example that not only does the size of the pipe change as the water flows through the pipe, but the height of the pipe also changes. So over here I have water that's flowing through this larger pipe that's down here at the bottom, and it's going to flow up into this narrower pipe that's up here towards the top. And the idea behind this is that because pressure is a non-conservative force, the work that is done by the pressure is going to be equal to the change in the energy of the water. So what I want to do is I want to consider this dark blue section of water right here, and I want to consider the work that is being done on this dark blue section of water, and then I want to consider the change in the energy of this dark blue section of water. And so I'm going to calculate the work that is being done on this water as the water moves up the pipe. So you can see here I've got these two pictures. This is the initial position of the water, and then after the pressure that is being exerted on the water moves the water, this is the final position of the water. So the water in this larger pipe is going to move to the right through some distance delta x1, and then in the narrower pipe over here it's going to have to move some larger distance delta x2. Okay, so that the volume that the water is displaced down here is equal to the volume that the water is displaced in the narrower pipe up here. So remember, work is equal to force times displacement. So the work that is done down here, I'm going to call this the work that is done in section 1, down here at the bottom, is equal to the force that is being exerted on the water, so that's equal to the pressure, P1, times the area, A1, times displacement, so we'll call that delta x1. And if we think about this, the area of the pipe times the distance that the water moves through, I have it shown down here, this is the volume that the water is displaced in this pipe. So we could write this as P1 times the volume of water that's displaced. Similarly, the work that's done in the top part of the pipe over here, now we got to be a little bit careful about this. So this pressure up here is going to be opposing the motion of the water. So the water is flowing to the right, and this force is pushing towards the left. So the work that's done by this pressure is going to be negative. But it's going to be the same thing. So it's going to be negative P2 times A2 times delta x2. And similarly, we can write this as minus P2 times V. Now you'll notice that I didn't put any subscripts on these volumes. The reason is that the volume of water that's displaced down here has to be equal to the volume of the water that flows through the top part of the pipe. This is by the continuity equation. The volume that water flows into the pipe has to be equal to the volume of the water flowing out of the pipe. So these two volumes have to be equal. So the total work that's done by the two pressures is going to be equal to, so let me write this down here, the sum of the work is equal to P1 minus P2 times the volume of water that moves through the pipe. So now let's go ahead and calculate the change in the kinetic energy. So I don't have this written here, but we'll say that this is going to be moving with a speed of v1, and up here it'll be moving with a speed v2. So the idea is that after some water flows up this pipe, we now have less water down here moving at the speed of v1, and more water up here moving at the speed v2. So the change in the kinetic energy is going to be equal to the kinetic energy that's lost by the fact that we don't have water down here moving at the speed v1, plus the kinetic energy that's gained by the fact that we now have more water up here moving at the speed v2. So this is going to be equal to the speed that the kinetic energy that we lose because we don't have water down here moving at the slower speed. So that this is going to be minus 1/2 m times v1 squared plus 1/2 m v2 squared. So we lost water that was moving down here at the speed v1, but we have more water up here moving at a speed v2. So this is the change in the kinetic energy. Now I want to rewrite this slightly in terms of mass density and volume of water, because we now, in the previous equation, right, I wrote this in terms of the volume of water that was displaced in this pipe and the volume of water that was added to this pipe. So I'm going to rewrite this in terms of that volume. So I could write this as 1/2 times the volume of water that's displaced in the pipe times the mass density of the water times v2 squared minus v1 squared. So this is the change in the kinetic energy of the water as it moves through this pipe. Now let's look at the change in the gravitational potential energy. So again, the same idea, we have less water down here and we have more water up here. So the change in the gravitational potential energy, well, we moved some mass of water from down here up here. So the change in the gravitational potential energy is going to be equal to the mass of the water that moved times g times the change in the height. So that's h2 minus h1. That should say h1. This is the height in section 1 of the pipe. So again, I want to rewrite this in terms of the mass density and the volume of water that moved from down here to up here. So that's equal to the mass density of water times the volume of the water that's displaced times g times h2 minus h1. Now finally, if we put all of this together, so we have, again going back, the work that was done is equal to P1 minus P2 times V. So we have P1 minus P2 times V has to be equal to the change in the kinetic energy, which was 1/2 V rho V2 squared minus V1 squared. So it's 1/2 times the volume of the water times rho times V2 squared minus V1 squared, plus, and then the change in the gravitational potential energy was rho Vg H2 minus H1. So we have rho GV H2 minus H1. Now again, we can see that the volumes are all going to cancel out. That's why I rewrote all of these things in terms of volume and mass density. And so we have that P1 minus P2, so the pressure difference is equal to 1/2 mass density times V2 squared minus V1 squared plus mass density times G times H2 minus H1. And if we want to, I can rewrite this. So I'm going to put all of the stuff that has subscripts 1 on one side of the equation and all the stuff that's describing the pressure and velocity in pipe 2 on the right side of the equation. So if I do that, I'm going to have P1 plus 1/2 rho V1 squared plus rho GH1 is equal to P2 plus 1/2 rho V2 squared plus rho GH2. So basically you can see that we have the same equation on both sides of the equal sign. The only difference is the subscripts. So what this means is that this quantity right here, pressure plus 1/2 mass density times speed squared plus rho GH, is always going to be equal to a constant. And this equation right here is called Bernoulli's equation. And so it turns out that we can actually use Bernoulli's equation to describe all sorts of really useful phenomenon. And one thing that I want to look at in particular is lift. So because Bernoulli's equation says that pressure plus 1/2 rho V squared plus rho GH is equal to a constant, If you have something where the height of the fluid isn't really changing, so this doesn't really matter too much, then what we have is that when air moves faster, pressure has to be lower. So there's a trade-off. When the air moves faster, the pressure will be lower. And this is the exact idea behind airplane design. So when you design an airplane, you design the wings of the airplane so that when the air travels over the top of the wing, it has to travel further so that the air has to move faster than the air that's traveling underneath the wing. So the idea is that because the speed up here on the top is faster, the pressure that the air exerts down on the wing over here will be lower than the pressure that is exerted on the bottom of the wing pushing up. So as a result, you'll have greater force pushing up on the wing than the forces that are pushing down on the wing. So how do we actually calculate this force? Well, it's pretty simple. We have the pressure that's exerted on the bottom of the wing plus 1/2 rho times the speed of the air at the bottom of the wing squared has to be equal to the pressure at the top of the wing plus 1/2 rho times the velocity of the air on the top of the wing. So this means that the lift force, which is the force that actually causes a plane to fly, it'll be equal to the pressure difference between the pressure that's being exerted on the bottom of the wing and the pressure that's exerted on the top of the wing. So that's the pressure on the bottom minus the pressure on the top. And then, of course, to turn this into a force, we have to multiply it by the area of the wing. And that'll be equal to 1/2 rho times the velocity of the air on top of the wing squared minus the velocity of the air on the bottom of the wing squared. And then, of course, to turn that into a force, I still have to multiply all of that by the area of the wing. So this is actually how airplanes fly. That's the basic idea behind it, is that you'll have the air moving above the wing is moving faster than the air below it, and as a result, there's a pressure difference between the top and the bottom of the wing. It's causing net pressure pushing up on the wing that'll counter gravity and actually allow a plane to fly. So let's go ahead and look at a few examples. This first example says, suppose that a 15 meter per second wind is blowing across the roof of a house. The density of air is 1.29 kilograms per cubic meter. The question asks us to determine the difference of the pressure caused by the air inside the house and the air that's outside the house. So the first thing that I want to point out about this is that, if we think about this, the air inside the house isn't really moving at all. It's going to be at rest. And we're told that the air outside the house is moving with a speed of 15 meters per second. So what this means, again, remember, is that if the air is moving with some speed v, then the pressure has to be lower, right? The faster the air moves, the smaller the pressure is. So this means that the pressure that's pushing down on the roof is actually going to be lower than the pressure that's pushing up on the roof. So what this means is that there's going to be a net pressure pushing up on the roof. And this is why, if you've ever seen a roof get torn off a building during like a hurricane or something like that, the roof is always lifted up into the sky and then it flies away like a kite. This is why that happens, is that what happens is that the pressure above the roof is reduced by the air flowing, and that causes the roof to get lifted up by the greater pressure that's underneath the roof. So let's calculate this difference in pressure. It's basically the same equation that we had for lift. So the idea is that we have the pressure on the inside of the house plus 1/2 rho times the velocity of the air on the inside of the house squared has to be equal to the pressure outside the house plus 1/2 rho times the speed of the air outside the house squared. And because the air is going to be at rest inside the house, this term goes to 0. So we have the pressure outside the house, the pressure inside the house minus outside the house will be equal to 1/2 rho times the speed of the air outside the house squared. And if we plug all these numbers into a calculator, we'll see that this pressure is equal to 145 pascals, which is a relatively small pressure, but when you think about the area of a roof, this kind of a small pressure difference can actually result in a relatively large force that can lift the roof off of a house. So let's go ahead and look at one more example. This example says, a small crack occurs at the base of a 15-meter high dam. The effective area of the crack is 1.3 times 10 to the minus 3 square meters. The question asks us to determine the speed that the water flows through the crack and the rate that the water will flow through the crack. So according to Bernoulli's equation, this quantity right here, P plus 1/2 rho v squared plus rho gh, is going to be the same everywhere. So all we need to do is find two places, and then we can set this quantity equal to each other at those two places. Now, because we're interested in finding the speed that the water flows out of the crack, one of the places where we want to apply Bernoulli's equation is this point right here. So the second point we should pick is wherever is easiest, and probably the easiest place we can pick for the second point is right here at the surface of the water. So if we think about right here at the surface of the water, the only forces that are pushing down that cause pressure at this point is atmosphere. So the pressure right here is just going to be equal to 1 atmosphere. Similarly, if we think about the water that's leaving this crack, the only force that's pushing against the water to kind of stop it is the air. So again, the pressure right here is going to be equal to 1 atmosphere. So this tells us the pressure. What about the height? Again, if you think about where this equation came from, we got this by applying the work-energy theorem. And just like gravitational potential energy, the height is kind of arbitrary. Where we call 0 height for this is also going to be kind of arbitrary. So what I'm going to do is I'm going to call this point right here, this lowest point, where the water leaves the crack, I'll call this h equals 0 meters. And then up here, this is going to be h equal 15 meters, since it's 15 meters above the crack. And if we think about the water right here at the surface, the water up here is basically going to be at rest. So unless you're really, really close to the crack, maybe the water right here is going to be moving a little bit, and really, really close to the crack, the water might be moving. But this is a lake, right? We're damming up a lake. So up here at the surface, this water isn't going to be moving at all. So we have the speed of the water up here is going to be 0. So I'm going to refer to this point up here, I guess, as 1, and this point down here is 2. So if we apply Bernoulli's equation, we have P1 plus 1/2 rho V1 squared plus rho GH1 is equal to P2 plus 1/2 rho V2 squared plus rho GH2. So we said that H2, that's this point where the crack is, we said that we're going to call this height equal to 0. So this term is going to be 0. And we also said that up here at the surface of the water is really not moving. So this means that V1 is going to be 0. So we have P1 plus rho GH1 is equal to P2 plus 1/2 rho V2 squared. Now the other thing we can do is that P1 is going to be equal to P2. Remember, these two pressures are just equal to atmosphere. So these two things cancel. So we have rho GH1 is equal to 1/2 rho V2 squared. Finally, we can divide off the rho, and we see that the speed that the water leaves the crack is going to be equal to 2GH1 square rooted. And if you plug this number into a calculator, you see that this is going to be equal to 17.1 meters per second. Now, one thing I want to point out about this equation, this is actually the same equation you get if you calculate the speed that an object would be moving after it falls a distance h. And so the second part of the question asks us to find the rate that the water flows through the crack. But remember that this is just going to be equal to, so we have a flow rate. Remember, this is equal to the area of the crack times the speed that the water moves through the crack. So this is going to be equal to 2.23 times 10 to the minus 3 cubic meters per second. So that's 2.23 liters per second of water moving through the crack. And so at this point, I think I'd like to end this video. And this pretty much wraps up the whole first half of this course. So after this, we're probably going to start reviewing for the midterm exam. And in the second half of the year, we're going to start up talking about electricity and magnetism.